Our final presentation today is from the Aerospace Engineering Department and is titled BANSHEE Project. This is a multidisciplinary effort to increase the mission capability of a hybrid airplane-quadcopter drone by improving its endurance and range. To meet this goal, the team is developing several novel technologies to recharge the drone's batteries during flight and reduce the aircraft's overall weight. I now invite the aerospace engineering team to share their presentation. Please.
Thank you everyone for coming here. So we are the BANSHEE UAV Senior Project. My name is Isaac Khan. I am the Deputy Project Manager. We are an interdisciplinary senior project with over 72 members from the aerospace, electrical and computer engineering departments and mechanical engineering departments. Our faculty advisors are Professor Stephen Dobbs from the Aero Department and Dr. Jenny Yu from the ECE Department. So unmanned aerial vehicles struggle with power limitations and limited weight requirements. They cannot exceed a certain amount of weight because they're meant to be small. So we would like to solve this by integrating two features on our flight vehicles. The first being solar panel wing skins on the upper wing skin, and on the lower wing skin we would like to use induction charging to allow our UAVs to fly above power lines and regain power that way. We are working with Southern California Edison on this, and in fact we have a couple members from them here today. So we are also utilizing a structural battery wing spar. This is to address that weight concern. We would like to make the weight of our wings more useful, so we are using a battery as the wing spar, and to address the concern of eventually our UAV will have to land. So we have an autonomous battery exchange system, that is the robotic ground system, that will allow our UAV to have its battery exchanged and be back in the air in less than 2 minutes. And of course, this requires no human intervention, which will allow us to maintain a long mission. Our Storm 4 quadcopter over here is our initial UAV that we have begun working with. This is to allow us to verify autonomous landing as well as the battery exchange process. Over here you can see our Cinch drone. That is where we begin integrating a Storm 4 quadcopter with a commercially bought Volantix ASW RC glider. This Cinch drone will be the vehicle that we are integrating our 4 new technologies on to test them. And then the Baby Shark over here on the right is the vehicle we will be using next year to test how well we have achieved these goals and the performance increase.
So I'm Maya Tene. I'm the design lead for BANSHEE, and this year the team proposed a number of new designs for the Cinch drone. As mentioned by Isaac earlier, the Cinch drone is a combination of an off-the-shelf glider with a quadcopter motor setup. This serves to really extend that endurance time while preserving battery. So shown here are our 2 current models in development. On the left is our current model, which is a Cinch drone fit with the phone wing. And this is implementing that quadcopter setup. And then on the right is our next phase, which includes regenerative wings housing structural batteries. And that includes those 4 new technologies mentioned earlier. So moving into the wing design, or the new design for the VTOL component. This entered redesign this year to really streamline that geometry, as the VTOL component is central to the system design. This includes kind of streamlining that way by including an aerodynamic nose insert made of expanding foam, and then utilizing the wind stream for cooling of that motor during forward flight. To combat vortexing, a carbon fiber flare was also included on that back end. These are the new regenerative wings. They feature a series of interlocking 3D printed wing ribs, which interface with carbon fiber spars. That entire assembly is then housed in a lower structural fiberglass skin, which is inlaid with an induction coil for power line induction charging during flight, and a structural solar top skin. Both of these are used to extend the endurance time by adding power input. And this whole assembly houses new batteries that are currently under development by the team.
All right, my name is Alec Justice. I'm on the structures and manufacturing team for the BANSHEE UAV project. And we have our cinch drone layout here with our 4 integrated technologies. We have our lower wing induction coils. We have our upper wing solar skin panels. We have the carbon fiber quadcopter spars along with our structural wing battery spars. And these are going to be the 4 integrated technologies that we implement on our cinch drone itself. But before manufacturing this, we did a couple of tests using ANSYS Mechanical. We did 2 types of tests. We did the static structural test and a vibrational test. These were both done on the wings of the UAV themselves with the focus of decoupling the first bending mode and the first torsional mode, because that would cause a lot of flutter. Right here on the left side, we have our completed cinch drone built with both carbon fiber booms that will house all 4 motors. And to increase the stiffness of the wings themselves and to decrease the overall weight, what we had done is we had replaced the original aluminum spar that was in the commercial Volantex, and we've replaced it with a carbon fiber spar. And that basically kept the rigidity the same, but it also decreased the weight in and of itself. Now, while in the air, due to the booms being on the ends, that increased the radius of gyration of the wings, causing a lot more torsion. And in order to combat that, what we had done on each wing is we had implemented a carbon fiber wing wrap. And that is basically just a wrap on the wings towards the fuselage. And that has been impregnated with epoxy and cured to provide torsional resistance. Now that we have a practical model, we did our practical test. We had done a physical stiffness test and compared that to the finite element stiffness in of itself. The experimental stiffness that we had come up with was about 919 newtons per meter, and the finite element stiffness that we had come up with was 904 newtons per meter, which gave us about a 1.7% error in our data, which basically confirmed that our test is practical and is ready for use.
Alright, so hi, my name is Shaman. Today I will be covering flight as well as ECE. So here's our Volantex ASW endurance test, where we are using this as a base model to create our cinch drone. So the main component of this is a Pickstock for Mini flight control unit that allows us to control aspects of the UAV during flight, such as the front DC motor propeller, as well as the servo motors that are connected to the wings. So over here on the left side, if we can do that. So we do see the autonomous flight path that we uploaded to our Pickstock for Mini through Mission Planner, and then we have proof of this flying here on the right. So we start off with a manual takeoff for a UAV, and then once we're able to stabilize it in the air, we switch it to an auto mode through our controller so that we'll be able to follow the flight path that we uploaded to it. We do get a total flight time of 13 minutes and 53 seconds, but by creating the cinch drone, we do intend to increase the flight endurance for this. Now here's the Baby Shark eVTOL endurance test, where we are going to be doing this with a completely manual flight. Over here on the left side, we do have the vertical takeoff for the Baby Shark, and then on the right side, we are transitioning from a VTOL to a fixed wing mode. We do get a total flight time of 15 minutes for this, but by adding the 4 technologies that Alec mentioned, we will be able to increase the flight endurance for this as well. Alright, so here's our robotic ground system, which allows for efficient battery swapping and, theoretically speaking, infinite flight time. So 3 main components: we have the ground control station, battery transport, as well as a battery vending machine. So the way this works is that the UAV has an onboard camera that can see the AR marker on the ground control station, which will allow for PID control landing, which we're seeing on the far left right here. From here, the robotic arm on the battery transport will be able to pick up the battery from the UAV, go across the ramp, put into one of the empty slots of the battery vending machine. Battery vending machine is going to rotate using a stepper motor and a gearbox, allowing the robotic arm to select a new fully charged LiPo battery, go back up the ramp, put it into the UAV, and allow for continuous flight from here. Lastly, we do have wireless induction placed within the ground control station, which allow us to power on the UAV's electronics during the battery transfer process. And this entire process will be taking 2 minutes. Now here's a proof of concept for the previous slide, where we see on the left the 2 gifts for the ground control station working. Top right we have the battery transport, and at the bottom right we have the battery vending machine. And Alec, if you can pick this up really quick, we have the chamber for our battery vending machine, where you have the 3 wheels that allow us to rotate on the actual battery vending machine structure, as well as 2 solenoid locks on both sides that allow us to Well, to prevent the battery from falling out during the actual rotating process. Now lastly, you do have the MEC station flight test, but the MEC station has the purpose of allowing us to see the live video feed from our onboard camera, the AutoCam. Three main components on the far left give right here. We have the 2-axis gimbal, which allows us to see the power lines as we are flying near them, as well as the ground control station when landing. You have the PC where you can see the live video feed through a wireless UDP connection, and the controller, of course, which allows us to control movements for our gimbal. In the middle, we have our quadcopter flight test with all the onboard gimbal components attached, and to the right of that, we have the live video footage as we are flying.
Thank you, Shadman. So our systems team this year has been working on a model-based systems engineering digital twin of our cinch drone. We would like to have a model that we can use to anticipate the improved performance. So here you can see our system diagram for a cinch drone motor. This will allow us to, of course, anticipate the performance of our battery, as well as what sort of thrust we can receive depending on what motors we use, and how the flight time given a certain battery. This is currently 60% complete, and we hope to utilize it before we complete the cinch drone to anticipate improved performance. So in summary, the cinch drone baseline model is complete. We are looking to now create the new wing, which Maya displayed, which includes our 4 new technologies, and that will before that happens, we would like to have a flight endurance test so we can have a number, how long our baseline cinch drone can fly, and then when we create the new model, what is the improved time and what sort of percentage improvement that is. We are aiming for 50% flight endurance increase. The robotic ground station is currently 80% operational, so before it's complete, we would like to test the battery hot swap process. And as well as that, we would like to have our Storm 4 UAV perform an autonomous landing without human intervention to test the whole system and the battery exchange process without having to have a human there to supervise. And our Baby Shark baseline endurance test is complete. This is preparing us for next year, where we will also want to be modifying the Baby Shark with our 4 new technologies as a final step for this project. I'd like to, of course, thank our sponsors, particularly Lockheed Martin, who has provided yearly support for us for a long time now. I'd also like to thank the Air Force Research Institute, who provided us the $10,000 grant that allowed us to purchase the Baby Shark. And, of course, Southern California Edison for allowing us to work with them and hopefully complete a power line induction test with them sometime soon. And our advisors, Professor Stephen Dobbs and Dr. Jenny Yu, for their advisement and expertise they have provided over these last few years. Thank you, everyone.